To use the first method for computing expected payoff, to find the mean of an ideal dataset of payoffs, we first need to find an ideal dataset to work with. That means a certain number of copies of each of these dollar amounts, so that that set of numbers is perfectly representative of what happens in the long run. Now, since the probabilities are given as two-place decimals, an easy way to find an ideal dataset is to multiply the probabilities through by 100, which means shifting the decimal point 2 places to the right. So in a perfectly representative 100 rolls of the die, there are exactly 35 copies of $10, 20 copies of $20, etc., all the way up to 5 copies of $60. This is a perfectly good ideal dataset, but we can make our lives a little easier by noticing that each of these numbers of die rolls is divisible by 5. So if we divide all of them by 5, we reduce the size of our ideal dataset from 100 rolls to just 20 rolls. To be clear, this means that in an ideal set of 20 die rolls, perfectly representative of what happens in the long run, there are 7 copies of $10, 4 copies of $20, 3 copies of $30, etc., all the way up to 1 copy of $60. Right? There are $20 amounts. To find the expected payoff, which is the long-term average dollar amount that we make per play of the game, we just take the ordinary average of these 20 numbers. We just add up these 20 numbers and divide through by 20. Here I've organized them in our usual way: $10 but 7 copies of it, plus $20 but 4 copies of it, etc., all the way down to $60 but 1 copy of it. All of that divided by 20, which turns out to equal $520 over 20, which equals $26. If we keep playing the game and averaging the results, we will make $26 per play of the game on average in the long run. Note that if the die were fair, each of these payoffs would be equally likely, and then the average would be right down the middle, $35. Instead, the probabilities are weighted towards the lower end, towards the lower dollar values, so the expected payoff is only $26, significantly lower than $35. By the second method for computing expected value, we relentlessly multiply payoff times probability of obtaining that payoff. We are finding the weighted average of the payoffs, where each payoff is weighted by its probability. So, $10 times 0.35 plus $20 times 0.2 plus $30 times 0.15. We're taking each payoff and weighting it by its likelihood of occurring. Plus $40 times 0.15 plus $50 times 0.1 plus $60 times 0.05. And don't forget the 0 in the 0.05. We have accounted for all possible values. If you count up the probabilities will add up to 1, as they must. And when you compute this, you will get $26. It has to equal $26. The two methods have to produce the same answer. Now, if you obtained different numerical answers by the two methods, you would know that you had made a mistake somewhere. This is another reason why it's good to have two different methods for computing the same thing. They give you a way of checking that your answer is correct. Note that we could have been asked to find not the expected payoff, but rather the expected number that appears on the die. Of the numbers 1, 2, 3, 4, 5, 6, we could ask, what's the expected number? What's the long-term average number that appears when you roll this unfair die many times? Then we'd set up a very similar computation. 1 times 0.35 plus 2 rather than 20 times 0.2 plus 3 rather than 30 times 0.15, etc. 4 times 0.15 plus 5 times 0.1 plus 6 times 0.05, and that will equal 2.6. That makes sense because the answer before was 26 when we took the weighted average of numbers that were 10 times greater. Whatever we're finding the expected value of, the principle behind the weighted average method is the same. value times probability of obtaining that value, plus value times probability, plus value times its probability, etc., relentlessly until we have accounted for all the values. What should it cost you each time you play in order for the game to be a fair game in the technical, mathematical sense? Knowing that, on average, you will receive $26 per play of the game means that it should cost you exactly $26. The casino should charge you $26 each time you play in order to bring your expected profit, your expected net gain, down from $26 to exactly $0. That is what fair game means in the mathematical sense, that the expected net gain is exactly 0. Caution! The word fair has two different meanings in this course. To say that the die is fair means that the outcomes are equally likely, and in our example, the die is definitely not a fair die. But to say that a game is fair means something different, and is all about whether the expected net gain is exactly 0. In our example here, we can make the game a fair game by adjusting the cost of playing and charging the player $26 per play of the game. So here we can have a fair game with an unfair die. The word fair just has two different meanings. Now, if this game costs anything less than $26, it will be profitable for you to play in the long run. But if it costs anything more than $26 per play of the game, you will lose money playing this game in the long run. And if it is a casino game, they will already have done this computation and made sure that they do charge you more than $26 per play of the game. This is why you should not go to the casino. So why is this important? We've figured out that $26 is the only amount the casino can charge you that will make the game a fair game in the technical sense of that term, so that everyone is breaking even in the long run. If it charges anything other than $26, then someone is making money and someone else is losing money in the long run. The bottom line is that expected value computations enable us to detect whether a financial decision like this one, whether to play this game or not, is a good decision or a bad decision in the long run.